Hi, I'm Jawed. Welcome to the presentation on model calibration in dense classification with adaptive label perturbation. Model calibration degree measures a model in terms of its prediction reliability. The prediction confidence of a well-calibrated model should reflect the chance of the predictions being correct. This is particularly important in critical applications where misjudgment based on overconfident input can incur severe consequences. We present an adaptive label perturbation method that tunes a per-sample label perturbation scale to calibrate the deep neural network model. In this sample, we use a stochastic version where each training sample is associated with an extra perturbed label, and the label sampling during training follows a Bernoulli distribution whose probability is adjusted per training sample. We first propose a self-calibrating binary cross-entropy loss that unifies a range of label augmentation techniques. Here, Z follows the Bernoulli distribution to sample from the ground truth label Y and the perturbed label P. The label perturbation probability alpha controls the frequency of sampling the two labels. Our method can be connected to maximum entropy inference that assumes a minimum distribution commitment in respect to missing information. Let's first state the channel entropy for binary prediction, which should be maximized in the complete absence of information. The proposed SCBC laws can be transformed into a factored combination of a BC laws with respect to ground truth label and the BC laws with respect to a binary uniform categorical distribution. Here, minimizing the second term equivalently maximizes the inference entropy. We divide the gradient by beta over 2 so that the convergence speed becomes the same for different label perturbation techniques. We present adaptive stochastic label perturbation that adjusts the label augmentation probability for individual training samples. First, we allow the variable z to be drawn from an image-wise Bernoulli distribution with sample-specific label perturbation probability. The label perturbation probabilities are initially set to 0, and we train the model with a regular BC loss until converge into a local minima. We denote its accuracy on the validation set as an ideal performance. The learning rule of the proposed ASLP has two components. The first component is the partial derivative of SCBC laws with respect to the sample-wise label perturbation probability alpha I. The second one is the regularization that maintains prediction accuracy denoted as reg A, or model calibration degree denoted as reg C. ASLP MEI incorporates the accuracy regularization, which constrains the validation accuracy not to drop below the ideal accuracy achieved. Here, eta is the learning rate of the label perturbation probability, and the lambda is the strength of regularization. Alternatively, ASLP MC adopts the calibration regularization, which specifically constrains the expected label confidence to not drop below the ideal accuracy. This is the framework of ASLP. Different stochastic label perturbation techniques can be selected by varying beta. In each iteration, either ground truth label or perturbed label is sampled to optimize the SCBC loss. When the prediction is correct, the gradient of alpha is positive, increasing the label perturbation probability, and vice versa. The regularization counters the increasing trend in light of model accuracy or expected label confidence dropping below the ideal accuracy. These two components eventually reach a balance that stabilizes the alpha. As shown in the figure, the mean label perturbation probability stabilizes after reaching a balance. Also, normalizing the gradient of alpha allows different stochastic label perturbation techniques to have the same convergence speed. We use equal with expected calibration error and overconfidence error to evaluate the model calibration degree on a binary dense classification task. In the model calibration degree benchmark on salient object detection, our method ASLP MC compares favorably against both the state-of-the-art SOD methods and the model calibration methods. In the joint distribution of prediction confidence and prediction accuracy, our ASLP MC is more aligned to the oracle line of perfectly calibrated model. It is also worth noting that despite producing a significantly underconfident model, ASLP MEI still maintains a high prediction accuracy. Our method can also perform well on out-of-distribution texture images where salient objects are absent. This table demonstrates the effectiveness of our various stochastic label perturbation techniques and their adaptive versions in calibrating the neural network models. We show that adaptive label smoothing, which can be similarly derived, is also effective in improving the model calibration. Thank you for your interest and attention.